coming in, so we won't get started with the super important stuff. But important is an update on the marking of the midterms. So I made a little miscalculation. Remember I said that the university gives us about 2 weeks in order to do all the grading, just to give you an idea about like what expected marking time is. And in my head, I was thinking that 2 weeks is today, but it's not because of Thanksgiving. So the 2 week kind of like, you know, usual marking time is the end of Wednesday. And we will do our very best to get them up actually on time. It is possible, because it's the first time that we're actually doing this amount of marking for a midterm, we may go a day or two over, so they will be up this week, unless there's some, you know, catastrophe.
They will be up this week.
They will be up this week.
Unless they're not.
Unless they're not. But...
And then they will be up as soon as we can.
Because I was looking at the marks going, oh, okay, it should be done by, you know, last night.
There was a lot, there was some panic.
There was some panic, yeah. Because the average was pretty low. It wasn't super low, but it was pretty low, and I was like,
surprisingly
what?
low.
And then I realized that
half the questions hadn't been marked.
No, not half. There's
many.
There's a good chunk that still needs to get done, so it is coming to an end. The majority of the questions have been marked. We just need another couple of days to wrap it up.
We share that story with you just so that you realize that exams cause panic on all fronts, all sides of that iteration.
Yeah.
There was panic. There were stress dreams about exams here.
Yes, but anyway, it's coming along really well. We do have the stuff that was automatically graded, like the true-false questions about the phylogeny. Those we've had since the beginning, and they look great. There were a couple that were a little bit harder for you, which is, again, really good to know where you're at. But for the most part, those tree reading, phylogeny stuff, were done really well. So yay you. And as soon as we have them posted, we'll release them so that you can all take a look.
So positive feedback wherever you're sitting. If you're sitting in a room by yourself, put your right hand up, reach around, pat yourself on the back.
Good job.
Well done, you.
Yeah, absolutely.
If you're sitting in a room with another person, get them to do it for you.
Cool. If you have any questions or whatever, open up your chat. We're actually going to be using the chat today a little bit later, so if you want to participate, we'll be using that, and we'll do some Zoom polling and stuff. And so there was some homework. If you remember,
It's all these people in.
Yeah. So I guess actually no, we should go back and admire the wonderful drawings that you've done, especially this one here. I think that one's brilliant. It's so good. I would totally want to have like spaghetti string all over my popsicle. I think it's awesome. But anyway, well done. And shall we delete? Shall we share it? Shall we save it?
I've shaved it.
You've saved it?
I have shaved it by the seashore.
By the seashore? Okay, good. And so we will clear all drawings, but we will be annotating for like real stuff. So hold on to those annotation menus. We'll get to that a little bit later.
Cap your pen.
Oh, here we go. Good. So homework.
Does it look like this where you are?
Oh, isn't it beautiful?
Mm.
Yeah. Lovely. Here we go. So here's your homework question. From all I can tell, these are new numbers. So even if you didn't do the homework, you should still, spend a few minutes trying to figure out this homework. And I will open up the Zoom poll for you so that you can indicate your answer.
I will be quiet.
Be quiet.
I will not sing.
We could put you on mute. Okay, I better figure out what the answer is. It's really cute.
That's interesting. The direction that that's going, it's interesting.
Why? Oh, that's not the answer. This is. Right? That's what I figured out. This one is competition, but this one, these two are competition for water.
Yeah, so they have low survivals. So
Weak. So water has a weak limiting effect on survival, whereas shade has a strong, so low light and high light that has a strong.
I think it's B.
Competition for water has a strong limiting effect, whereas high light levels promote survival.
The weirdest is weird. But it's like those are the lowest survivals. With competition for water, there's no competition for water. Highlight. No.
Let's see. Yeah. Okay. Hello. Okay. Good. 90% of you. Wonderful. That's great. So we will end polling, and you've done well. I will share the results. So the results are, the answer is C. And I mean, basically it comes down to B or C, so well done. Very important though, when you're trying to figure out what the answer is I will open up the annotation, because what I would like you to do is, for those of you who are wondering, why is it C and not B, or why is it C and not any of the other ones? It's really a question that relates to, using different tools of logic thinking to be able to figure out which ones you need to compare in order to figure out what the effect of water is or what the effect of shade is. So if you wouldn't mind, imagine that we were trying to figure out whether or not light was important, or shade, right? The amount of light was important. Which two of these three would we compare in order to be able to isolate the effect of light? Yeah, good. Okay, that's really, really good. Super, super, super. Okay, you can stop. So in order to isolate the effect of light, what you need to do is to, I will just clear all drawings. You need to compare the one where the condition of water is the same, right? Because if you compared A and B, it would be really difficult to isolate because both conditions are different, right? So A and C both have competition for water, right? So that's kind of a baseline. And then one has high light and one has low light, so then you can figure out what the effect of light is, right? All things being equal, and that's where all things being equal come. It doesn't have to be all things being good or all things being bad. They just need to be equal, right? So competition for water or water situation between A and C is the same. Now, if you're going to be trying to figure out the effect of water, which two are you going to compare? Yeah, really good. Okay, so I think you're getting it. You would compare B and C, and then if we take a look at B and C and what the actual effect is, let's just clear all of the drawings. So both of them have highlight. That's the all things being equal. There's no competition for water, and there's competition for water, and you can see that it's 70 to 85%. So a weak effect potentially. Much stronger effect though when we're talking about light. Is that good? I hope. Okay. It's so weird. But yes, I feel like you're nodding. I hope you're okay.
No one in the chat.
No one in the chat is asking.
Nodding.
Okay, everybody's like, yeah, good. Okay, cool. So let's move on. Stop the annotating. Here are our learning outcomes that you can take a look at later. What we're going to do today, essentially. And
there will be zombies.
There will be zombies. Yeah.
Zombies.
But first, I think there are moose.
And some moose too. So we're talking about carrying capacity, population density and carrying capacity. Maybe your brain's already going to where we might take zombie examples within that. But before we get to zombies, we wanted to talk about moose in a Canadian example. Did you know, those of you who have perhaps been or maybe even are from or have family from Newfoundland, that moose, you know this if you're from there, moose are not native to Newfoundland. The first moose was taken to Newfoundland. This is it. They took a picture. 1906, the year this house that we're sitting in, our lecture theater, the year it was built, they took a moose to Newfoundland. It did well, because about a decade before that, why did they do it? For food, literally for food. They had extirpated wolves the year before, well, the decade before, which was a bit of a problem, because other than people then, there were no other predators. There was just a limiting factor of how much the moose could eat, and it turns out a lot. If you don't know this, an adult moose weighs somewhere around 1,000 pounds. That's a large animal. There were 4 of them dropped off in 1906. The current estimates have over 100,000 of them. So it's like 100 million pounds of moose now roaming the island of Newfoundland. This is, it would be great for food, and there's certainly a healthy license and a hunt, but it doesn't do anything to control the population. And if you've driven around the island, you know yourself that there's a danger to the human population because the moose are on the road. And when you have the equation of moose plus vehicle plus speed equals bad. So population carrying capacity, population density, and the carrying capacity of a certain area, these are real problems. They're not just esoteric. They're esoteric, that'd be like a problem that has a non-right angle.
I like that. That's good.
So it's a real thing.
Yeah.
And sometimes it's delicious.
We had you thinking a little bit about some of the different variables that you can measure at the different levels of organization and which ones are relevant. And so what we wanted to do is kind of like overload your brain with all of the variables that we could think of that are kind of relevant to the conversation of population level. And they are really quite specific to population level. And hopefully, kind of once you allow your brain to dive in deeper to what we mean by population. What do we mean by population?
Well, think about that hierarchy that we talked about, the biological hierarchy. It's something above an individual and beneath a species. So individuals of the same species.
Oh, you put species in that list?
I do.
I don't.
Ah,
I just go straight to community.
I know, but
Wow.
community is nothing without a species. But anyhow.
Oh, but species is like an abstract concept.
Oh, but it is so not.
Oh.
We're going to have a large philosophical discussion. I'll bring my Aristotle. You bring your Plato.
Wonderful.
Da, 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 da.
Anyway.
Ask your parents about what that was. Ask your grandparents.
My grandparents. Okay, good. So,
but this is important. Like Dr. Jacobs this is important because the level that we're talking about here is important, and the examples that we come up with here that you're probably already thinking about, and I mentioned in the moose example, like the area of the island. These are ones that are specific to the population level. They don't matter so much at the individual level, and they matter less so at the species level. Yeah. And not at all at the biome. Right.
So, distribution, that's a thing. Where are they on like 2-dimensional or 3-dimensional space?
Dear Google, what is the volume of Newfoundland?
Nice. Okay. That's something you can measure with a population.
Dear Google, how many moose are there?
You can definitely count the number of moose. You can count the number of moose per area.
Dear Google, divide the first number by the second.
Exactly. You can calculate their birth and death rates, so how that fluctuates over time. You can calculate or take a look at their sex and age structure, males versus females. We're talking about sex, not gender, just to note for any future biologists, when you use the words, be precise.
Yes.
Fecundity, so number of eggs produced per female.
Fecundity.
Fertility, different than fecundity.
Yes.
Fecundity. Fecundity, number of eggs that produce viable offspring. Production, different, number of offspring produced by a population. And recruitment, again, like these are basically going through sort of the stages of natural history, right?
Yeah.
And at every point there is some like falling off, right? Some death, okay? So
Yep.
from fecundity to fertility to production to recruitment, you lose. That number is gonna be smaller, okay? Fecundity is gonna be the highest number, recruitment is gonna be the lowest number. Yeah, it cannot be the other way around.
Now, there are some ways that species affect this, of course. So these numbers will be species specific.
Yes.
So they will be different for a moose than they will be for a wood turtle. If you're a wood turtle, it's very hard to make it out of your first year. But once you do that, you may live 100 years.
Right.
But a moose, not so much. You might make it out of your first year, and then you've got a very different kind of chance of mortality as you live along.
Along highways.
Along highways and without a shell.
Yeah.
Moose with a shell. Oh, note to self.
Okay, so it depends, right? When we're talking about different species, okay? So here's just another example where, you know, you can change the scale and you can change what a lot is, right? A lot is a super relative number. So you can have a lot of ladybird beetles, and we're starting to see those coming into our apartments and our houses, right? As the weather gets colder and colder. And a lot could be, 50 per meter squared, for example. Diatoms, though, first of all, we're not just talking about meters squared, we're talking about meters cubed. And a lot could be 5 million in a meter cube, right? So everything just depends on its body size and how much space it needs in order to be able to survive. And that's really connecting it to carrying capacity, right? How much of an organism or of a species can that space hold, right? So in order for them to be able to continue to thrive and survive.
Remember, that intersects with some of what we were talking about last week in terms of the fundamental and the realized niche. An update from that there are survivors of moose crashes in our audience.
Oh wow, that's so scary.
Yeah, super scary. So well done, you.
Yeah.
And don't do it again,
No.
please. And the other one is that somebody likes to spring upon people, and I like that you spring facts upon people. I imagine you on a bus in pre- and post-COVID times going, guess what? And that one of the predators for the moose is the killer whale.
Whoa!
Which is, of course, true. If you are a moose out for a swim,
Yes.
yeah.
And they do swim.
Yes, they do.
Yes.
Really well.
Yeah.
Because they've got feet.
Really big paddles.
What are diatoms? Diatoms are a complex bunch of little shell-secreting things that are very tiny, animal-like, plant-like, and they live in freshwater and marine systems.
Yes, and they're gorgeous.
And they are gorgeous.
A
And this-
photo right
yeah.
here of a whole bunch of them.
So we look at those, they're called tests, those little shells. So we look at those tests to figure out things, how things are living, and then also we can go into sediment afterwards and examine those tests or shells to find out how that has changed through time. Super useful.
So useful.
Yeah.
Okay, so
Nice, underscore.
populations over time, really simple. You add up the number of births and you subtract the number of deaths.
Whoa, 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 whoa,
And and then you take a look at immigration and emigration and you're done. For those of you that need to see this visually with some pretty pictures, here we go. Population at time 1, right?
T1.
T1, population P, T1 time 1, right? Which means that it is more than time 0 and less than time 2, and we'll show you how to use those, that annotation, okay?
So the population at T2,
Yes.
if it goes up,
If it goes up, or,
that's going to be because of those factors.
yes. So if there are births and immigration, population at time 2, which is when you measure it the second time, is going to increase. Super simple, right?
Right? You got that.
Population at time 2, if it goes down, is going to be a result of either death or emigration, right? So either they leave or they die. And then your population is going to go down.
So arrivals on top of two kinds, departures on the bottom.
That's right.
Of two kinds.
Yes. So at time 1, time 2, you can take a look.
And if you can estimate those, you can balance those in the following very intuitive
Yes.
sentence. Let's not even call it math. The sentence that's right there.
There's no way that I could like remember that equation. You just talk your way through it, right? You add and you subtract. But
I think so yeah, it's not, think of it as a sentence.
Yeah.
So if I want to know the population at time 2, I need to know the population before.
Yeah.
And then I'm going to add the births minus the deaths. So that kind of specific to the individual arrivals and departures. And then I'm going to add the movement, who's arrived by movement, who's departed by movement.
Yeah. So don't really worry about memorizing this equation. If you understand the concepts, you'll be fine. And we will give you some homework a little bit later to actually, get you to play with these numbers and to kind of remember which one is which.
Can I do another thing here? One of them is that this is super quick, but it's also, remember about the moose. We can estimate these things for moose, but it's still very hard to do, even though moose are, as we say, 1,000 pounds, and we know a lot about them, and you can survey them from the helicopter. So I'm just tying into a species level again, going, for some species, we know these parameters and we can make these calculations, we can form these sentences. For many species, which are smaller than a centimeter, we don't have any idea at all. And we can't survey by helicopter, we just take fun helicopter rides.
That's right. And if you can't remember the difference between immigration and emigration, talk about genius, it took me a while, but I is for in, E is for exit. Super simple. Okay, that's how I remember it. I swear, every time in my head, I have to do this.
I think we need a thinking cap.
That was good, right? Okay, super simple. Okay, so once we know how many there are, another thing that we can do is take a look at distribution. So that was another variable that was on our list, okay? And distribution is kind of neat. You need to set the limits of your space. Okay, and we'll show you how you can play around with the limits of the space and why that actually matters. But once you define your space, so defined in this particular case by these 3 boxes, right? Once you define the space, you can take a look at the way that individuals in your population are distributed, okay? And they can be clumped, even, or what some people call random. And again, if you're interested in biological philosophy, there's a whole area of that. I do not fall into the category of people that think that there is random distribution, but maybe, do you?
I think it's a great starting point. It's like a null model that you would test out what you've observed it against.
Okay. So random.
Diatoms.
Maybe. And maybe not. It depends. Maybe you're just looking at the wrong scale, and we'll show you exactly how you can play around with scale in order to.
What is the acronym WTF? Why that for?
So clumped, first of all, really cool. Clumped tells you so much about the biological properties of the organism that you're working on, as well as some of the abiotic distributions of things, right, within the environment, which is super cool. Clumped is usually associated with resources, things that the species needs in order to be able to survive. The idea is that it would be closer to those things.
Yep, and we're prone to seeing clumped things. We like to have hand-wavy explanations. So we look at toads on a landscape and say they're clumped because they need water, or frogs on a landscape, or butterflies at patches of flowers. Those are clumped. So lots of associations with resources.
That's right. And then even has a lot to do with competition and spreading out those resources, right? So the idea is that some things, try to get certain habitats or certain territories and need to defend them, and therefore the kind of limits of the individual territory are halfway between where one individual is and where the other one is.
Have you talked about your bird example?
No, I haven't, but I have a really cool photo.
I love that one.
Okay, so random, honestly, I don't get it. And maybe this guy does a little bit more.
So I think that it does exist, and I think, again, I personally am inclined to look for it or evidence of it because I think we have a bias to seeing clumped things. And so we explain things very quickly because, oh, it's because of this, and I see this, and I see this, and then we don't ever test those things, but we're like, yeah, it's clumped because I see this. It's like, but did you see it really?
Okay. I just think, anyway, fine. Yes, it's all
Tune
good.
in later and we can talk about clumpy random distributions.
I think the student hour is going to be really, really busy.
It's clumped.
It's clumped. Okay.
Some observations.
Yeah.
Can a population increase if death rates decrease but birth rates stay the same? That's a great question. And yes.
Good job. Okay, so birds and even distribution, and it is fascinating. So the photo that you see in the middle here on the bottom is a gannet colony, a colony of northern gannets, and they are beautiful things that have built-in airbags in their faces to be able to like absorb the shock of hitting water as they torpedo into it in order to catch fish. It's awesome. You should watch videos of gannets all day long.
G-A-N-N-E-T.
Yes.
Yes.
Okay. So you can see just by looking at the top of the colony that their distribution is pretty darn even. They are like in lines of equal spacing.
Yeah, people went around planting gannets.
Almost looks like a plantation of gannets. So what's going on here is super simple. That distance between one nest and another nest is exactly about 1 centimeter longer than the two bills of the gannets, right? So they're going to be like trying to peck each other, and they just can't because the space is just big enough so that they can't kill each other as they try to occupy their own little territory. Okay, same thing goes with penguin colonies, except for penguin colonies are a little bit wider than just 1 centimeter beyond their bill reach. They're actually exactly the width, the gap is exactly the width of a penguin who's walking quickly with its wings backwards because they can't just land on their nest, they have to walk to their nest, okay? So all of these things, though, create even distributions. Right?
How many of you rocked in your seat like a waddling penguin
Waddling
when
penguin,
just you say the word waddle penguin walking?
Okay, so yeah, and then...
Just me.
Just you.
Good.
Yeah, okay. So what we want to ask you is this. Which of these patterns corresponds to a human distribution?
And there's some thoughts about human distribution in the chat that we haven't answered because or talked about yet because
Hold on.
Yeah.
Yay. Okay.
Oh, I like.
Well done. Well done. Well done. Random. Nice.
Oh, a question. Great question.
Yeah.
What scale?
That's good. Keep that in mind.
Good question.
Okay. So
yeah, it came up twice.
that's
good for you.
Really, really good. Okay. So question for you, and
Look at
that
big purple circle.
Big purple circle. Okay. Question for you then. If we're talking about clumped, what scale are we talking about? So if you want, just write a word, a couple of you, or put it in the chat. When we're talking about a clumped distribution, what scale are we talking about? What scale corresponds to clumped distribution?
Some thoughts. Local is popped up. Global.
By city, super good. Global, super good. Okay.
City to city.
Amazing. Household, nice.
That's really important.
That's really good. Totally different, right? Okay. Good.
Clumped around rivers as a source of water.
Excellent.
Yep, certainly.
Excellent.
As we settled here.
So when we're talking about even, what scale are we talking about?
A thought in the chat applying to farm and rural areas.
Nice.
Streets.
Residential. Super. Yay. Okay, we're done for the day.
Yeah.
Yeah, well done. Local. Good. Okay. Good. And then I have no idea what you're going to say for random, so surprise us, because I don't get random. I don't get random. Tell me what scale is random. I have no idea.
Global. Okay. And I think some of those other scales, somebody says people in the forest, shows such as Survivor.
I love that.
Those
Off-grid
weird border areas between city
yeah.
and countrysides.
Okay. Yep. Rich people. living where they want.
And we
Amazing.
could, yeah, you could.
That's pretty good.
You could release a bunch of people into a new house, and then they'd kind of
randomly
move around
until they settled next to resources.
Yeah.
And then they would be clumped.
But it would have been so then the scale. You talked about scale. We imagine you might have been thinking, and I think some of you were, about spatial scale. Temporal scale matters too.
Okay. Are you gonna save this?
I always save it.
Okay. I'm gonna clear it then, because we're gonna move on. You guys are awesome. Here we go. Clear all drawings. We've saved it. We'll post it so that you'll have your responses there.
And of course, your chat responses are there too.
Yes, so good.
So thinking about spatial scale, we can do a free fall drop with those. What's the drink people? The caffeinated drink. Red Bull. So come with us to the Red Bull Plain, high above Southern Ontario, and we'll just jump out.
Okay.
And at this scale, what are you seeing? How clumped, how maybe this is, as you start falling through space, you're looking, look at that clump distribution!
Yeah, super clumped,
all around
right?
water!
All around water, ports of entry, essentially, right? People colonized and occupied and settled the Americas based upon where they could get their ships, right? There were already people living here, also in a clump distribution for very different reasons. But the colonization of North America was done in a clumped way according to where ports of entry could be from ship-based access.
Now, as you fall through space, kind of your Red Bull plane, and you get closer and closer, what does that change?
A lot.
Yeah.
Right?
And hopefully you've pulled your chute by this point.
So you've totally nailed the distribution, that it changes depending upon your scale. And what I love is that one of you said, there we go, thanks Colton, super even. And territory based, right? This is my territory, here's my fence, right? Don't mow my lawn, I'm mowing my own lawn kind of deal. And then within the household, I love that at least one of you noticed that it changes again within the household, right? Most of the family is usually around the kitchen area. At least mine is, yours is, and then we kind of spread out a little even at night, and then we come back into this clumped scenario again. So.
And you remember probably pre-COVID times, you've experienced this going to houses for parties that nominally were at somebody's house, and inevitably, at least in my experience, they end up in the kitchen.
Yep.
You have a kitchen party.
Kitchen party.
Yeah.
Okay. So, yes, it depends on the scale, right? Okay.
La, 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 la.
Carrying capacity, then.
Could we say that humans have become less clumped as technology has increased? Like we are building cities in some more unconventional places. That's interesting.
Yeah.
I would maybe join with you in thinking about the fact that could happen, but I think in most cases we're just intensifying where we already were.
Yeah.
And kind of leaking out the sides. If you've flown into Calgary before, Calgary, which doesn't have any kind of natural hard border like the island of Montreal or the ocean adjacent to Vancouver, and so Calgary just kind of leaks until eventually it's going to bump into Saskatchewan. But most other places get more intense.
Yeah. So yes.
But technology can certainly affect this kind of thing.
Yeah.
Yes.
Yeah. Your phone's ringing.
We're closed.
Okay. Carrying capacity. So. How many individuals can a specific area, and remember, you have to define your area, support, right? That's carrying capacity. If we take a look at sort of the history of population growth or the history of a population growing, once it sort of enters a region, enters a space, or settles, or colonizes, or invades, you can use all of these words. There's kind of this classic shape, this classic trend, right? This ecological relationship that we talk about. And it looks like this. It looks like this S-curve, right? And at some point in the middle, there's this little dot here. And if you want to throw down in the chat what the name of that dot is, that would be great. Or you can write it on the screen somewhere that's not like right on the words so that other people can read. But basically what we've got on the x-axis is time, and on the y-axis we have population size. Thank you, Colton. Point of inflection. That's really good. And the idea is that over time, obviously the population size is going to grow, but that's not the only thing that's happening, right? Because it's a curve. So it means that the rate of growth is going to change as well, okay? And it's at the point of inflection that that rate really goes from super, super high to starting to peter out. It's that point where the rate changes, right? From an increasing rate to a declining rate over time, okay? It doesn't mean that the population decreases, but that the rate of growth decreases. And I think for the first time in a long time, all of us are pretty familiar with the term exponential growth, right?
Why would that be?
Why? Yes, here we go, where concavity of rate of growth changes, exactly. So it goes from being a high exponential growth to a lowering growth that eventually will reach zero growth at maximum population size, which is your carrying capacity, okay? And that, of course, that where that line is can change depending upon the context, on the environment, on a whole bunch of abiotic and biotic factors. And so we're going to talk a little bit about the implications for carrying capacity and how we can actually change carrying capacity within an environment. But first, in the chat, what I would love, so that other people can then go and see, is that you pick a point and describe something that could be happening to that population in that moment if you go out and measure the population and you find it at D, for example, or B, or C, or A, or E. What could be happening to that population or to the environment that would cause you to measure the population at that point? Oh, good. So, yes, thank you. At A, population is newly introduced to the environment. Good.
Yep.
At point E, it's already at carrying capacity. Super good. B, births are greater than deaths. D, new subdivision being built. Super. So I suppose you're going to be talking about some other species than humans. At D, something comes in to like curb population growth rate, right? To slow it down. Super good. C, resources are starting to limit growth. Excellent. D, resources are starting to decline overall. Yes.
Yep.
Super good. C, government rules about babies being born. Yeah, sure, for sure.
Yep.
C, rate of population growth slows. A large group of population was wiped out and the population is starting to increase in size again. Yes.
Yep, good scenario. So you're invoking time earlier.
Yes.
Lovely.
Exactly.
D,
So,
more competition.
more competition. Very good, right? So basically you can slide up and down, which I love by some of your answers, where you can kind of go back in time. You can have like a bottleneck effect, right? That dramatically reduces the population, was going to bring it back down to A, and then the population is going to spring back up, okay? According to this theoretical curve. So super well done. And if we take a look at the history of humans,
See that
yeah.
certainly you can change these things. So we talked in the last slide about as you move up and down that growth curve, that certain parameters can change, meaning you move in one direction or the other. So you can see across contemporary human history that the numbers bubbled up and down, up and down. There was a big crash associated with the bubonic plague. And then significant changes, positive changes in the number of people on the planet, associated with first with the Industrial Revolution, and then next essentially with advances in medical technology that allowed us to live longer, and for more of us to live through the first year of life.
Yep. Okay.
Somebody asked in the chat, is coronavirus a product of us reaching our maximum population size? That's a big question. I'd say a short answer is no. But the coronavirus is a product of a whole bunch of things.
Yep.
A whole bunch of things. We would need a course to talk about those things.
Yep. So that's an excellent segue into talking about density dependence and density independence.
So what kind of factors could change the directionality of a population, and how are those associated to the size of the population at one time, which is kind of, so density dependent things, which is kind of what your question is invoking, or things that are doing it independent of the size of the population, density independent factors.
Right. So this can be, again, like you're gonna have to kind of allow your brain to like target in on exactly what we mean, precise, right? Language. A density dependent population control is more effective in denser populations. So not necessarily in abundant populations. We're talking about populations that are dense, because the way that population control mechanism works is by potentially by like touch or face-to-face contact and those types of things. So coronavirus, right, is a density dependent virus, where if you were standing more than 6 feet apart, or well, 12 feet apart, you wouldn't be likely to get it. So the coronavirus is a density dependent population control virus, right? It's also a pretty weak one in that it's not, super lethal, but the lethality of it is based on density dependence, okay? So the idea is then that the mechanism is dependent upon the density, right? Okay. It's hard to explain because it isn't necessarily about absolute numbers, right? The idea is you could have a population of 1 million people, but if it's not dense, it's spread out, then this population control mechanism is not effective. If you take those 1 million people and you bring them together, then it becomes very effective. Similarly, you could have a population of 5 people, and if you spread them out, it won't be effective, and if you bring them together, it will be effective. So it doesn't matter the total population size. What matters is the density of that population. Whereas density independent, so examples like the coronavirus or like the plague or like a whole bunch of other things, right? Okay, whereas density independent, its effectiveness doesn't matter at all on the density of the population. So it is density independent, okay? So it works or it doesn't work no matter what, irrespective of the density. It has nothing to do with the density if you're trying to figure out whether or not it's effective. So again, if you have 1 million people spread out, or if you have 1 million people together, the effectiveness of whatever that treatment is going to be the same, right? It's either going to work or it's not going to work. And so it is separate or independent from density. And it's way easier to kind of think about this in terms of examples. But don't allow the example like of a hard freeze, if you're talking about a crop, for example, frozen, like, sub-zero temperatures is going to work whether all of the plants are together or all of them are separate, right? It's density independent. It doesn't matter.
Give yourself, as you juggle or struggle and juggle with trying to figure out the difference between these two things, think about, this is one case where I'd say maybe think about your own species as an example and think about how this would affect Churchill, Manitoba. Little tiny town on the north shore of Hudson Bay, or on the southeast or western shore of Hudson Bay, on the north side of Manitoba, and then put the same effect into the city of Toronto, or something very, very dense.
Yeah.
So what would happen with a hard freeze and affecting of a crop blown out in that we were dependent upon in Churchill and in Toronto? Kind of the same thing. If there's no food, both of those things happen. Whereas if there's a communicable disease and we're spread out across a large landscape in Churchill versus in the downtown, in the metro of Montreal or the subway of Toronto.
Okay. Or we could think about it in terms of a zombie apocalypse. So, question for you, think about it for a second, is would a zombie apocalypse, don't write anything yet because we've got like some buttons for you to push, okay? Would a zombie apocalypse represent a density dependent or density independent human population control? So imagine that there's a zombie apocalypse. This is the population control mechanism, is the zombies. Is it density dependent or density independent. We'll just give you like 30 seconds to like figure out what the argument is for why it's whichever one you pick.
Boom, 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 boom.
Okay. Are you ready? Boom. Okay. What's that? Oh, and there's a little spelling mistake that I did correct in a previous version. But go ahead and put your stamp where you think it is. I fixed it. I don't know what happened. Okay. Density dependent, I think, is the primary vote. And let's think a little bit about what the argument is for why you're saying density dependent. So if you could stop annotating, that would be great. Okay.
Some questions about the scenario in the chat.
Yeah.
What caused the zombies to appear?
Good.
Virus, something else?
Good.
I think usually dependent, but it could depend.
Yes, so let's talk about that in just a second. If you could stop annotating, I'm having difficulty catching up on my screen. There we go. Clear all drawings. There we go. Okay. So think about what the argument is and what the mechanism is, and we'll start first with density dependence. If you want to just write on the screen what the argument is for why you say it was density dependent. What is the mechanism
If you
that
don't
would
see it
make
appearing
it
there,
density
throw it in the
dependent?
chat as well.
Oh yeah, you can put it in the chat.
Also.
Virus-like zombies don't move fast, more brains in cities, that's nice, I like that. More effective in dense populations, spreads between individuals, the more people, the more zombies, the more people to eat
R0.
equals more people.
Why not?
Oh, super, good. Okay, aside from potential virus, competition with fellow survivors, super good, okay. Spread through biting. Yes, that's it, I believe. So contact would spread faster where there are more people. Very good, very good. Yep. You have to make sure that you're getting the right reason for why you say it's density dependent. It's not necessarily that that there are just more people in that space. The idea is that it is spread through contact, through biting. Which is face-to-face, right? Just like coronavirus is. So it is density dependent in that if there are no people around for a zombie to bite, then you're good. Except, and I happen to be like a huge zombie fan, so like I'm totally, yeah. I know, sorry.
No, you have to, no. I'm just calling you on it. You have to be very specific of what kind of zombie.
You totally do. What do you mean? Like all the zombies. There's like a lot of zombies. Okay, so the bite to bite is a density dependent mechanism, but that's not the only way that you can get zombified, right? So let's go back to the density independent. And what could the mechanism be for a density independent zombie apocalypse? Haitian zombies, nice. Spores, airborne, they have guns. In food or water supply, excellent,
Yeah,
yes.
super.
Yes.
So you're getting at the mechanism
right.
of transmission.
Yes,
Super
okay.
good. Super
good.
Super duper.
Like in The Walking Dead, yeah, thank you! That's it, exactly, right? So for the first part of The Walking Dead, spoiler alert, it's like the
if you
first
don't want to hear this.
I feel like you're all up to date, right? Okay,
it's half their life ago.
Spoiler alert, you can just like la 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 for 30 seconds. There, okay, so for the first part, we think that it's density dependent until it's not. Is that okay? That wasn't like a huge spoiler? Okay, so.
Can we do a quick poll on who's happy Carl's gone?
Yeah, okay, yes, so also, Z. What? No! Okay, Z Nation, right, also seems to be a density independent mechanism. I haven't watched any updates on Z Nation, so I don't know if they changed it up.
Do you mean Z Nation?
Oh, but yeah. Similarly, World War Z, right, is density dependent.
Yeah.
Those are fast zombies. and not everyone has it. So yes.
So they have rage. They're not, yeah.
Yeah. So it depends, right? Whether it's density dependent or independent, not on the condition of zombie, but on the way in which you become a zombie, okay? It matters, that mechanism. Is it close contact? If it's close contact, it's going to be density dependent. If whether you're in contact with somebody else or not doesn't matter, then it is, yeah, World War Z is so good. I just finished the audiobook. Oh, love it. Okay.
So different.
Yeah, and way better.
Author is Mel Brooks' son.
Oh, good. Yeah. Okay.
So the other, and you can go through now that we've parameterized you, we've filled you with this kind of search criteria, go through the zombie oeuvre and say, okay, so Shaun of the Dead, which you should all watch, is that dependent or independent or both?
So imagine, next question to kind of tie this all together. Imagine you're in the United States and there has been a zombie apocalypse, and you go and you collect data on the distribution of zombie outbreaks, okay? And you have to decide whether or not it is density independent or dependent. What I'm going to do is I'm going to show you that distribution map, and I want you to vote on whether or not you think that it is density independent or dependent. Are you ready? Go. Okay. Super good, right? Outbreaks are happening in the dense areas, but there's something that's a bit confusing. Which one is confusing? Which state is confusing to you? Very good. Okay, amazing. What could be going on there? The idea is not to allow your brain to focus on the outlier, on the exception, and say, well, then there's no rule here, right? What it does is it causes you to write another hypothesis, right? So yes, it's predominantly density dependent, but what's going on in Nebraska? What the fuck, Nebraska, right? I see it there. Exactly. So what could be going on in Nebraska? Yes, good, Madison.
Someone in the chat says, Nebraska is weak.
No. But good. So I think it was Madison that wrote traveling, right? Yeah. Maybe a whole bunch of people got out of New York and just went to Nebraska, and it
didn't listen to the advice from public health officials.
That's
it's like
right.
As if this isn't some kind of esoteric scenario, as if this is kind of a real thing.
Okay, so it could have become dense, right? After time, right? The population at time 1 went to population at time 2 increased, right? Due to immigration, for example.
There was a presidential rally.
Oh, that's funny.
Yep.
Thank you. Okay.
Oh, they had a wedding.
They had a wedding.
A lot of conventions.
Yeah. So, why is this a map of the U.S.? It was the only meme that I could find quickly.
No, but also we have better healthcare policies currently, so it stops at the border. Border's closed. Sorry, zombies.
Closed. Yeah, actually, we should. That's fair enough. We should totally switch to a Canadian map, and then it would just be this little sliver down along like Lake Ontario and a bunch of places, right? And then the rest would be.
I'm attracted to the idea that the wall on the southern border stops
the zombies. Okay. Thank you. So we're just trying to like get you to kind of like get your brain to walk through some of these different concepts and what evidence might prove or might support one versus another, to kind of learn how to apply these things. I hope it was helpful, and thank you for indulging me in the zombie world.
Now it's not even just an indulgement, and this is a slide that we made like pre-COVID. We talked about this even last when the course was offered in the winter term. COVID had not happened by this point as we were talking, and so we talked about the fact that CDC has this kind of they've responded to the public's interest in zombies, like not post-COVID, but post-George Romero, coming up for the first time with the idea of these zombie kind of scenarios. Really, as a social criticism was Romero's thoughts. CDC, the Center for Disease Control, uses the zombies as an example to plan for disease and to plan for pandemic and outbreak.
Yep. or you can play around with zombies quite seriously. Some biologists like to use them because, again, it's kind of cool.
So that URL up at the top, and I'll put it in the chat here in a second, is a live one where you can change various parameters of zombie, of the virulence, the time that it takes you to change, all sorts of things. I do love most of those films at the bottom there.
Yep.
The Revenant might be my favorite one.
I know.
No, Shaun of the Dead is my favorite one.
Is it? Yeah. Okay.
For two very different reasons. I like the soupçon of old world sadness in The Revenant, and I like
Bill Murray.
Yeah, that's a good one too.
Zombieland. Okay.
Yeah.
Go. Save yourselves. Here's your homework. Thank you very much.
Stop talking to
we have to
now?
stop talking. We're actually over time, and we get really excited about zombies. Here's your homework.
Watch all those films.
You can go through the questions. Here's a graph that we want you to make of a whole bunch of different lines and conditions, and
I'm going to put some of those
then we're going to
links in
follow
the
up
chat.
with a zombie homework question on Wednesday morning. So take care, everyone, and
Take care of each
around.
other. Be kind.
Yep. If you want, stick around for the
Expect
student
it
hours.
and deliver it.
Okay.